Hey everybody, this is Dr. Scott. We are here to talk about the scariest, the most dreaded topic in all of chemistry class. It's known as significant figures. Now, why? Why do you care about significant figures? Well, if you happen to be in a chemistry class, every time you get a right answer, you're going to get -1, a point taken off if you don't do this. So it's an important thing. You don't want to have -1 for otherwise correct answers. You want to learn sig figs. I'm going to show you the easy way. We're going to go through a simple 2-page worksheet. I'm going to show you everything you need to know about sig figs in just a few minutes. And if you happen to be on my website, you'll find a printer-friendly PDF version of this worksheet. You can print it out, follow along with me. This is going to be easy. We're going to get sig figs down in a few minutes, and then you're never going to have to think about this again. Okay, so we're here on the worksheet, page 1. The first exercise is to learn how to count sig figs. And the problem here is that the number 0 may or may not count. All other digits are going to count. So let's just go down through and learn the rules about this number 0. We have to first start the number 1. There's one digit and it's significant. We have the number 11, a 1 and a 1. There's two digits. They're both significant, so there's two sig figs in the number 11. Now, next we have the number 110. The rule is that trailing 0, the 0 to the right, does not count as significant because there's no decimal point there. Zeros to the right don't count unless there's a decimal point. So we have a 1 and a 1. There's two significant figures. Now, what that's saying is 110 is not really 110. It's a number somewhere between 100 and 120 that's maybe rounded off somehow to 110. And you can compare that with the next one. Note that we have 110 dot. Zeros to the right, these trailing zeros, they count if there's a decimal. Now there's a decimal, all of the digits are significant. And I just want to point out that this dot at the end is kind of a silly trick that chemistry professors came up with. I used to be a chemistry professor myself. I apologize to the world for this, but we have 110 dot, meaning that those zeros at the right are significant. There's a better way to do this using something called scientific notation. I have a separate free course on that, but that's another topic. So let's move on. We now have 111. There's three digits. They're all non-zero. All three are significant. Next, we have 111.0. There's a 0 at the end. It counts because there's a decimal point. So we have all four digits being significant. 111.00.00. Both zeros are significant because there's a decimal point. There's 5 digits total. They're all significant. Same idea with the next one, 111.000. They're all significant. Zeros at the right are significant. If there's a decimal point, there are 6 significant figures. Next, we have 1.000. There's a bunch of zeros to the right. There's a decimal point, so they are significant. All 4 digits are significant. Next, we have 1.001, and we have this case of the zeros being in the middle. Zeros in the middle always count. The first digit's 1, the last digit's 1. All digits in between count. So there's 4 significant figures there, maybe for a little bit different reason than the previous one. Now, next, going up to the next column, we have a different case, 0.001. And digits to the left never count as significant. There's just one significant figure there, the last one. And note that that's very different. Zeros at the right count if there's a decimal place. Zeros to the left just never count. So next we have 0.011. The 1 is significant. The zeros are not. There are 2 sig figs, 0.111, The 0 doesn't count, just the 0.111. Zeros to the left never count. It has nothing to do with the decimal point. 3 significant figures. The next one, 1.111, has 4 digits that are all non-zero, so they're all significant. And now we have 1.001. Looks like maybe we got a repeat there, but same idea. The zeros in the middle always count. The next couple, 11.001, all the digits are significant. The zeros are in the middle. They always count. 111.001. Again, there's ones at the beginning and the end. The zeros are in the middle. Zeros in the middle always count. We have 6 significant figures. Now next, we're coming back to some zeros on the right, which don't count unless there's a decimal point. So 111,000 has 3 significant figures. It's not actually 111,000, but it represents a number somewhere between 110,000 and 112,000. It's basically kind of rounded to the nearest thousand, if you will. Same we could say with 111 million. Zeros to the right don't count. Only those first 3 digits, the ones, count. And note that 111 million sort of means a number between 110 million, 112 million. Next, we have 11 million and 1, which represents a number between 11 million and 11 million and 2. It's a lot more precise, more to the point. The zeros are in the middle. There's ones at both ends, so all the digits are significant. That gives us 9 sig figs. So let's move on now to the second page. Now that we know how to count sig figs, let's see how we use them. Okay, so we have now some math problems, the type of problems you're likely to actually see in a chemistry class. And this is basically going to cover all possible cases of what's going to happen with sig figs in just 6 short examples here. So first, we're going to look at addition, and we have 2.2 plus 1.1. And now, when we're adding or subtracting, it's actually got nothing to do with the sig figs. We want to track the decimal places. I'll maybe refer to that as the DP, the decimal places. And 2.2 has 1 decimal place. 1.1 has 1 decimal place, so our answer needs to end up with 1 decimal place. So if we add 2.2 and 1.1, we get 3.3. That number has 1 decimal place in it, so that is the right answer, 3.3. It turns out, by the way, that 3.3 has 2 significant figures, but the rule is based on keeping the decimal places consistent for addition. Now note in this second example, the first one has 2 decimal places, but the second one has 1 decimal place. We're going to keep the smallest number of decimal places. Our answer just needs to have 1 decimal place, right? So if we were to add these in a calculator, we'd get something like 3.34, and you're thinking that's the right answer because it all adds up, but one of those numbers had 1 decimal place. We need to round this answer to 1 decimal place. So this 4 is wrong. You're going to get -1 if you put that on a chemistry exam. In chemistry, 2.24 plus 1.1 is 3.3. We need to round it to 1 decimal place. Now, this next problem here, you'll notice that both of the numbers being added have 2 decimal places. There's a 0.22, a 0.18. The answer needs to have 2 decimal places. And if we add them together, 2 plus 1 is 3, so we're going to get 3 something. 22 and 18 is 40 for what it's worth. If you put this into a calculator, it's going to say 3.4, but both numbers had 2 decimal places. 3.4 is wrong. You're going to get -1 if you put that on a chemistry exam. It's 3.40, which implies a more precise number than 3.4, which is why it's wrong. Let's go up now to the second column. We've got multiplication or division. we're going to do the same idea, keeping the fewest number of sig figs. So note that 10.0 is going to have 3 significant figures. I'll maybe write that as an SF, where 1.0 has 2 of these significant figures. So our final answer needs to have 2 significant figures. Now, it's basically 1 divided by 10. The answer is a tenth, which would be 0.1 as a fraction. And if you put this into a calculator, 1.0 divided by 10.0, it's going to say 0.1. That's wrong. Your answer needs to have 2 sig figs. We need to put a 0 at the end. 0.10 is the correct answer. 0.1 is wrong. You're going to get a -1 on that if you don't have an answer with 2 sig figs. Now, the next thing we have is 3.5 minus 3.0 over 3.0. And you're going to see this a lot in chemistry. We have something to the extent, something that sort of looks like A minus B over B, where A and B are different numbers. You see the next example, 4.0 minus 3.0 over 3.0. That's kind of similar as well. This comes up a lot in chemistry, especially when you're computing a percent error. Big opportunity for -1 on this calculation. So let's get it straight. This is kind of the important one for what it's worth. So we got to do the subtraction first in the numerator. 3.5 minus 3.0 is 0.5. And note that 0.5 has 1 sig fig. And we're going to divide that by 3.0. So if you haven't done it yet, get out your calculator. I'm going to get out my calculator. And let's type it into the calculator here. 0.5 divided by 3. You can type in 0.0 if you want. And what you're going to get out of the calculator is something like 0.1666666. It's actually what's called a repeating 6. It goes on forever. And this is one of the reasons we have sig figs, because repeating numbers are pretty annoying. We can't write down an infinite number. We need to round it. So how are we going to round it? Well, notice that 0.5 had 1 sig fig. We divided it by 3.0, a number that had 2 sig figs. And so our answer needs to have 1 sig fig. We need to round it to 1 non-zero number. The answer is 0.2 because it has 1 sig fig. And note that we started with numbers. 3.5 has 2 sig figs. 3.0 has 2 sig figs. We start with numbers that have 2 sig figs. Our answer has 1 sig fig. We've destroyed a significant figure, and that's what can happen when you see this type of expression, A minus B over B. You're actually supposed to, quote, destroy these sig figs, start with 2 and end with 1, sometimes when you see this. Now let's look at the next example. We have 4.0 minus 3.0, which would be 1.0 over 3.0. And now 1.0 and 3.0 both have 2 sig figs. So our answer needs to have 2 sig figs. If we put that into a calculator, it's a third, right? It's going to show 0.33333 repeating. We need to round it to 2 non-zero numbers. 0.33 is our final answer because it has 2 significant figures.